AP Chemistry, we're moving on to Lesson 7 of the Acid Bases unit. This has to do with an important topic, and that is buffers. So what is a buffer? A buffer is a conjugate acid-base pair designed to resist changes in pH if small amounts of a strong acid or strong base are introduced to the solution. So a very important example of a buffer is blood. Human blood contains a buffer, carbonic acid, and its conjugate base, the bicarbonate ion. And it does that in order to maintain a blood pH of between 7.35 and 7.45. A blood pH value higher than 7.8 or lower than 6.8 can lead to death. So the carbonic acid neutralizes any invader base. I call them invaders because they're coming in and you don't want them there. So any invader base that comes into your blood will be neutralized by the carbonic acid. That will prevent the pH from going up. And any invader acid coming in will be neutralized by the conjugate base, the bicarbonate ion, and that will prevent your pH from going down into the acid range. So it protects from both directions, both the acid and base directions. So buffers can be created from a weak acid that will neutralize the hydroxide ion, that's the base, and a weak base that will neutralize the hydronium ions, those are the acids. Neutralize means, we'll define it in just a short while, but it means that you create something that's neither an acid nor a base. The most common neutral substance is water, but it can be other things as well. Neutralized hydronium and hydroxide become neutral H2O molecules. Buffers must be created from a conjugate weak acid, weak base pair. It has to be a conjugate acid and base because conjugate acid and bases are like brothers and sisters. They have an equilibrium that they reach where there's a certain amount of the acid, a certain amount of the base, and so they don't want to react with each other. A random acid-base pair will react with each other in unpredictable ways and cannot act as a buffer. So all you need to really remember out of that, you don't have to explain why. Just remember that a buffer must be a conjugate weak acid, weak base pair. That means an acid and base that differ by exactly one proton. Conjugates of acetic acid and the acetate ion can act as a buffer because they're conjugates. The weak acid, acetic acid, CH3COOH, and the fluoride ion, which is a weak base, cannot act as buffers because they're not conjugates. They will react with each other. Acetic acid and the acetate ion are a conjugate acid-base pair. The acetic acid, CH3COOH, buffer defenders will guard against the strong base invaders. So we're going to use a metaphor of armies here. So here are hydroxide ions. Maybe they came from sodium hydroxide or potassium hydroxide or some other strong base. They want to invade that solution. Let's just say it's just pure water, and they want to raise the pH of the solution. So if they jump in, the pH is going to go up into the base range. So these are weak acid molecules. They're acetic acid, and they're defenders of the solution. So they want to protect the solution from pH change. So we talked about if you put that weak acid, acetic acid, in that water, some of it will dissociate to the water molecules, a very small amount. But what it will always dissociate to is a hydroxide ion. A weak acid, such as acetic acid, will totally dissociate and neutralize a hydroxide ion. It will send a proton, it will donate a proton to the hydroxide. The hydroxide will accept it, and it will then have two hydrogens and an oxygen, which creates a water molecule. So that's how acetic acid will neutralize the OH minuses. So it's a one-to-one relationship. It's one acetic acid molecule for one hydroxide ion. So we'll see that they're going to have a battle here. So when a defender fights an invader, both will neutralize and no longer exist. As long as there are more defenders than invaders, the solution will be protected and the pH will not change. So here they go. They're going to go to battle, and those two neutralize, those two neutralize, and those two neutralize. So all the hydroxide ions are gone. There are still a couple of defenders left. So the defenders won that one, and the pH didn't change. So there are no invaders left, but there are 2 defenders, so the pH remains unchanged. Now, you did use up some of your defenders doing that. If more OH came in, you would not be able to resist the change in pH for very long because you only have 2 defenders left. The solution also has acetate ion defenders to protect against strong acids, but they are not needed in this reaction. Okay, so now we're going to attack from the other side. These are the H+, the hydronium ion invaders from a strong acid, for example, hydrochloric acid. They want to lower the pH of the solution into the acid range. So on the other side of the buffer, you have the acetate ion, CH3COO-. So these are the acetate ion defenders of the solution. They want to protect the solution from pH change. So the CH3COO- buffer conjugate base defenders neutralize the H+ strong acid invaders by accepting a proton until one of the 2 runs out. So now they're going to go to battle again, and those 2 neutralize, those 2 neutralize, those 2 neutralize, neutralize, neutralize. When a defender fights an invader, both will neutralize and no longer exist. This time, there are more invaders than defenders, so the invaders win and the pH of the solution changes. So with all of the buffer defenders gone, the remaining strong acid invaders are free to pass protons to water molecules, and that creates hydronium ions, H3O+ ions. This will lower the pH down into the acidic range. So there they go. The invaders are going to jump in the solution, and they're going to create hydronium ions. So of course, they were already in the solution, but in our metaphor, we're acting like they were trying to attack the solution from the outside. Okay, so there they are. Now the solution becomes more acidic. pH will hold only as long as there are more buffer defenders than invader strong acid or strong base. Salts. So to understand buffers, we have to define a couple of new terms. One of them is a salt. When a hydrofluoric weak acid molecule dissociates, it produces its conjugate base, which is the fluoride ion F-. This is a reversible reaction, so the fluoride ion base can take back the same proton or a different one. So again, with weak acids, they can give off the proton, but then they can also take it back. When they give it off, you have the fluoride ion. That's a conjugate base of hydrofluoric acid. When the proton returns, it turns the particle back into hydrofluoric acid, HF. So that is a reversible reaction. So the fluoride ion F- is the conjugate base of hydrofluoric acid. A salt is a neutralized acid or base. Neutralized means that it's neither an acid or a base. So to neutralize an acid or a base means you turn it into something that's not an acid or a base. The most common neutralization would be a water molecule. Now I know we say oftentimes that water can either be an acid or a base, but in a general sense by itself, it's neither one. It's a neutralized. If you think about it, you put an H+ ion together with an OH- ion, that's a hydronium and a hydroxide, you put them together, you have a water molecule. They've neutralized each other. A salt is formed when a 1+ cation, such as sodium, Na+, and you just have to go to your charge number by ion sheet, or just remember how elements ionize. We talked about that back in the ionic bonds unit. So a salt is formed when a 1+ cation, such as sodium, Na+, which takes on a 1+ charge, attaches to the conjugate base F- or some other weak base. So the Na+ and the F- form an electrically neutral ionic bond. Positive, negative attract each other. This bond will only form out of water, but will dissolve 100% of the time when you put it into water. So again, let's think of that. What you did is you had a hydrofluoric acid. A proton left it. It went away. That was a +1 charge.
you substituted that proton for a sodium ion, which is also a +1 charge. So they're both of them, they're electrically neutral. The difference is a sodium attached to a fluoride ion is not an acid or a base. It's a neutral substance. It's neither an acid nor a base. So that is what's called, so the fluoride ion, F- and any cation such as Na+, form a basic salt, a neutralized base. So that's called a basic salt. It's formed from a base, F-, but it's been neutralized. It's no longer a base, so that's called a basic salt. Again, the word salt means it's neutralized. NaF is called a basic salt because it is formed from the neutralization of a base. An acidic salt is formed when a weak acid is neutralized by an anion, such as a chloride ion. So a weak acid has will have, in this case, well, let's take this example. Here we have ammonia, NH3, and that molecule is a weak base and can accept a H+ proton from the water molecule. So we're going to see that happen right here. So some of the time, not all of the time, it's a weak base. A proton will jump from the water molecule over to the ammonia molecule. It'll create a conjugate acid, NH4+. It's a conjugate acid of ammonia. So it's positively charged because it accepted a proton. The water molecule lost that proton, so it's now a hydroxide ion, and that's the definition of a base. It's a solution that has hydroxide ions in it. Okay. An acidic salt is formed when a weak acid is neutralized by an anion, such as a chloride ion, Cl-. Again, we'll go to your charge number by ion sheet, and you'll see that Cl- is a 1- charge. So the ammonium ion, NH4+, has a 1+ charge. Now, if you take a chloride ion, it could be anything from the halogen group, which will produce 1- charges. That could be fluorine, a fluoride ion, a chloride, a bromide, an iodide ion. They all form 1- charges. So the chloride takes 1 electron to form a 1- charge. So there you see the chloride will be attracted to the ammonium ion. That's a positive charge and a negative charge. So an acidic salt is formed when a weak acid is neutralized by an anion. The ammonium ion, NH4+, has a 1+ charge. So now what happens is the NH4+ creates an ionic bond with the Cl- to form ammonium chloride. So that's now a neutral molecule. You've neutralized a weak acid with a with a chloride ion, and therefore you've created a salt, and that's called an acidic salt because it's a neutralized acid molecule. NH4+ is an acid molecule. So this molecule is called ammonium chloride. It is a neutralized NH4+ acid molecule. A neutralized acid molecule is called an acidic salt. So let's review. This is something we did in previous lessons. Hydroxide ions, such OH- has such a strong pull on protons that it will cause 100% of weak acid molecules to dissociate. So there you have hydrofluoric acid on the left. It's a weak acid. So in water, only a small number of those protons will dissociate to a water molecule. That's the definition of a weak acid. But in the presence of a hydroxide, they will all dissociate. So this means that every strong or weak acid molecule that enters the water will give a proton to a hydroxide molecule, really hydroxide ion. Okay? So that was a weak acid with a strong base, with OH-. Now we're going to look at a strong acid with a weak base. That's the fluoride ion is a weak base. It will weakly attract protons from water molecules. But what happens when you put it in solution with a strong acid? A strong acid, HCl, is placed in aqueous solution with a weak base of F-, the conjugate base of hydrofluoric acid, HF. Will the proton donate to the water molecules or to the fluoride ions?
So we know that a strong acid, HCl, will 100% of the time dissociate to those two water molecules right there. The question is, which would it prefer, the water molecules or the fluoride ions over on the right? So the strong acid, H plus protons, will first dissociate to the weak base fluoride ions, F minus. Okay. So you had 4 strong acid molecules and 4 fluoride ions, and the fluoride ions neutralized the HCl. So what you really did there, if you think about it, is you took 4 strong acid molecules and traded them in for 4 weak acid molecules. Now the strong acids will really turn the solution acidic because it will dissociate to water molecules 100% of the time. But the weak acid molecules, the hydrofluoric acid that you now have over there on the right, will only occasionally dissociate to a water molecule. So you've traded something that will always dissociate to a water molecule and create an acidic solution for something that will only occasionally, very, very rarely dissociate to a water molecule. So what the fluoride ions did is they neutralized the strong acid molecules. Now, if you still have a strong acid molecule left after all the F minus ions have been used up, then that will dissociate to a water molecule and create a hydronium ion and turn the solution into an acidic solution. So let's read this. The strong acid HCl is placed in aqueous solution of a weak base F minus and the conjugate base HF. Will the proton donate to the water molecule or the F minus ions? So the strong acid H plus protons will first dissociate to the weak base fluoride ions, F minus. That's their first choice. Only after all the fluoride F minus ions have been consumed does the HCl dissociate to the water to create hydronium ions. So what that's saying, again, is that the weak base, F minus, will neutralize the strong acid. Only after you've used up all of the F minus, then will the strong acid, HCl, dissociate to a water molecule. So to create a buffer, how do we do it? We need to do several things. First, you need to choose the pH you want to hold stable. So for blood, for example, it was between 7.35 and 7.45. First, though, you choose the pH, and that would be 7.35 to 7.45. Next, you choose a conjugate weak acid-base pair with an acid pKa equal to the desired pH. Okay, we're going to get into that concept in a later lesson. The third thing you do is you use an equal number of moles of weak acid. The third thing you need to do, and this is what we're going to do in this lesson, is you need to use an equal number of moles of a weak acid and its conjugate base salt. Or you could flip that around. You could use an equal number of moles of a weak base and its conjugate acid salt. We're actually going to, in our example today, we're going to do 3A. We're going to take the weak acid and its conjugate base salt to create equal numbers of the acid and the conjugate base. So we will use a weak acid, hydrofluoric acid, and its conjugate base, the fluoride ion. So that's going to create our buffer. The hydrofluoric acid is going to guard against base invaders coming into the solution, and the fluoride, the F minus, is going to accept protons from acids, so it's going to protect against acid invaders coming into our solution and changing the pH. So first, we need to produce an equal number of moles of hydrofluoric acid and fluoride ions, so we can guard against equal numbers of strong acid and strong base. So you want an equal number of molecules or moles of the hydrofluoric acid and the fluoride ion. So if you look down below, you see 5 hydrofluoric acid molecules. So we will use simple numbers and say that 1 out of 5 hydrofluoric acid molecules will dissociate to produce F minus ions. That's in pure water. The number is obviously much, much smaller than that, but we're trying to keep the number simple. So we're going to say that 1 out of 5 hydrofluoric acids dissociate. So you see that that just happened. You now have 4 hydrofluoric acid molecules and 1 fluoride ion there. The proton we don't care about at this point. It went off somewhere to another molecule. So this would represent the equilibrium concentration in this example, not in the real world, but in this example of hydrofluoric acid and the fluoride ion. You have 4 hydrofluoric acid molecules for every 1 fluoride ion. So the equilibrium concentrations of hydrofluoric acid and fluoride will serve as a buffer. 4 times as many strong base molecules can be neutralized as strong acid. So if you look at that down there, you have 4 hydrofluoric acid molecules. They're going to guard against bases. They're going to neutralize hydroxide ions. So the HF weak acid will guard against 4 molecules of invader strong base, say sodium hydroxide, for example. Over on the right side, you only have 1 fluoride ion. It's going to guard against an acid. It's going to accept the proton from a strong acid and neutralize it. So the F- ion will guard against 1 molecule of invader strong acid, such as HCl. But the thing is, for a buffer, we would like these numbers to be equal. We would like to guard just as much against a strong acid as a strong base. So we somehow need to add more of the fluoride ions, the F-, so that they equal the number of hydrofluoric acids. So how can we do that? How can we create more fluoride ions? So the problem is, if we add more hydrofluoric acid, we will produce more fluoride ions. However, the ratio of hydrofluoric acid to fluoride will continue to be 4 hydrofluoric acid to 1 fluoride. So if I do that, now if I add 5 more and 5 more and 5 more, I continue to have a 4-to-1 ratio. So yes, I'm adding fluoride ions, but I'm also adding more hydrofluoric acid molecules, and I don't want to do that. I want the numbers to be equal. So I didn't do anything to make those numbers equal simply by adding more of the weak acid hydrofluoric acid. So how do we add fluoride ions without adding more hydrofluoric acid molecules? So that's the problem we have to solve here. So how do we add more fluoride ions without adding more hydrofluoric acid molecules? The answer is we use the conjugate base salt of hydrofluoric acid, the one that we looked at earlier, and that's sodium fluoride, NaF. So we will add 5 sodium fluoride base salt molecules to the solution. So there we go. There's 1, 2, 3, 4, 5. Now, what do we know will happen when you put NaF in water? What happens immediately? The sodiums will break away. Your solubility rules tell you that. Okay, according to solubility rules, the Na+ ions completely dissociate from the fluoride ions. So now what you have is you now have 1, 2, 3, 4, 5, and even 6 of the fluoride ions there. Okay, that's how you got more fluoride ions without putting more hydrofluoric acid into the solution. So now we see that NaF and HF both produce a common ion. That's the fluoride ion. So we did common ion problems a couple lessons back, and this is why we did them. Did those problems, because we're going to use them in creating buffers. So now we actually have 4 hydrofluoric acid and 6 fluoride ions. So we actually have more fluoride ions now than we have hydrofluoric acid. But from our earlier common ion problems, and according to Le Chatelier's principle, the concentration of fluoride ions is greater than equilibrium. Okay, remember the equilibrium was 4 hydrofluoric acids for every 1 fluoride. Now you have way more than that. You have 6 fluorides and 4 hydrofluoric acids. So remember what Le Chatelier's principle said that would do. You have, on the product side, on the fluoride ion side, you have way too many for equilibrium. So this will push the reaction back toward the reactant side, the hydrofluoric acid. So the excess of fluoride ions above the normal equilibrium concentration will push the reaction back to the left to create more hydrofluoric acid molecules. So watch this happen here. So there's the reaction in simplified form, and it's going to go back to the left because you have too many of those F- on the product side. So there goes the fluoride ion. It's going back over to the hydrofluoric acid side, and from somewhere it's going to associate with a proton that'll come from somewhere. And now you have a hydrofluoric acid molecule again. That's because Le Chatelier's principle says the reaction is going to get pushed back to make more reactants. There were too many products, F- molecules, so the reaction went backwards. So we accomplished our goal. We have the same number of hydrofluoric acid as fluoride particles. This is how to create a buffer starting with a weak acid. So a buffer, here's the thing to remember, a buffer is created by using a weak acid and a salt of its conjugate base. So you can't just keep putting more of the weak acid in of the hydrofluoric acid to get the fluoride ions. You'll never get them to be even. So what you did is you went and got the salt of the conjugate base, in this case sodium fluoride. The sodiums broke away and they went off to the side, and the fluorides therefore increased in concentration until they were equal with the hydrofluoric acids. So now we have a buffer that will defend equally against bases, that would be the hydrofluoric acid molecule, and against acids, that would be the fluoride ion over there on the right. So the buffer can now guard against OH- or H+ invaders equally. A buffer from a weak base can also be created in the same fashion, but we just did this one example of creating a buffer from a weak acid. Okay? So that takes care of this lesson. So that's the first step in how do you create a buffer, is how do you get equal numbers of an acid and base in the solution so that you can protect against both an invading acid and an invading base. Okay, we'll learn the other steps in the next lessons.